Okay, moving on to boiling points and solubility. So we can compare the boiling points of various organic compounds using their polarity. So that's the important part. Okay, so using their polarity and the intermolecular attractions between the molecules. So for boiling point, the general rule is that the bigger the molecule, the higher the boiling point. The reason why that's a general rule is just because London forces typically have a bigger effect on boiling points. And for London forces, the rule is the bigger the compound or the more mass the compound has, the more London forces you're going to have. Okay, so if a molecule also has hydrogen bonding, so if it has more modes of intermolecular forces, such as alcohols and carboxylic acids, that's also going to increase its boiling point significantly. Okay, so with this table here, essentially it's just trying to show you the trend. So looking over here, we have ethane, propane, butane, pentane, hexane. So in other words, we have a compound with 2 carbons in it, 3 carbons, 4 carbons, 5, and 6. So ethane also has 2 carbons. Propane has 3 carbons, 4 carbons, 5 carbons, 6 carbons, so on and so forth. So within this table that shows us homologous series between alkanes and alkynes, just notice that as we go down the table for both of these homologous series, the amount of carbons are increasing. In other words, the size of the molecule is increasing as we go down this table. And as you notice with the boiling points within each homologous series, the boiling points, as we gain more carbons, the boiling point is increasing both in the alkane homologous series and the alkyne homologous series. So ultimately, this is just kind of proving the point of the bigger the molecule, the higher the boiling point. Okay, so notice what happens to the boiling points once there are functional groups attached which contain hydrogen bonds. Okay, so they've got a table here comparing hydrocarbons, alcohols, and carboxylic acids. So if we look, okay, in the first row here, all of these compounds, they all have 6 carbons in them. Okay, but hydrocarbons, when they're talking about that, they're either talking about alkanes or alkenes in this table here. With alcohols, that functional group is the hydroxyl. Okay, so the squiggly line just means like some sort of carbon chain is attached to the hydroxyl or the OH group. And with carboxylic acids, that functional group is this. So that's the COOH functional group. Okay, so as we go from hydrocarbon to alcohol to carboxylic acid, notice how the boiling point increases. Okay, so essentially what we can say is that hydrocarbons such as alkanes have a lower boiling point, or have a trend of having a lower boiling point compared to alcohols and carboxylic acids. So let's just write that over here. So for boiling points, an alkane has a lower boiling point than an alcohol, which has a lower boiling point to a carboxylic acid. Okay, as long as you're comparing, like basically this assumes that you are comparing all these different functional groups with the same amount of carbons in each compound. Okay, so the reason why alcohols have a higher boiling point compared to a hydrocarbon is essentially because it's polar and it can hydrogen bond. The reason why carboxylic acids have an even higher boiling point compared to alcohols is, yeah, it's polar and yeah, it can hydrogen bond. And the reason, like, even though they have the same intermolecular forces, the reason why carboxylic acid has a higher boiling point than alcohols is because it's a more polar molecule, because it has more electronegative atoms in that carboxylic acid functional group. Okay. So again, if we compare cyclohexane to cyclohexanol, the alcohol has the higher of the two boiling points. Okay, cyclohexene, compare that to cyclohexanol, again, the alcohol has the higher boiling point. Once we're comparing benzene with phenol with benzoic acid, so again, benzene is just a 6-membered ring with alternating double bonds, whereas phenol would be that same benzene ring, okay, but it just has an OH attached to it, okay? And then benzoic acid would be that 6-membered ring, but let's see if I can squeeze this in, but it has the carboxylic acid attached to it, okay? So again, alcohols and carboxylic acids, they're going to have higher boiling points than either alkanes or alkenes. So maybe I should adjust this a little bit, and we'll just say alkane / alkene. There we go. All right, moving on to this first example here. Place the following organic compounds assuming the same number of carbons in order from highest boiling point to lowest boiling point. Okay, so we have alcohol. Aliphatic just means that it's a carbon chain, carboxylic acid, and then an ester. Okay, so the first thing that we want to do is just figure out, okay, what intermolecular forces are happening here. So with alcohols, you have London dispersion forces, or London forces, because everything has a London force. Okay, you're going to have dipole-dipole attractions because alcohols are polar compounds. And then this can do hydrogen bonding because, again, because of that OH group, the alcohol group, hydrogen is directly attached to oxygen, which contributes to hydrogen bonding. With aliphatic, it's just carbon chains. There's no special functional group like hydroxyl, so an OH, a carboxylic acid, or ester. There's no special functional group that makes it anything other than a chain of carbons and hydrogens. Okay, so this is just going to have London forces. With carboxylic acids, so again, a carboxylic acid is that COOH functional group. Okay, so that's going to have London forces. It's going to be able to have dipole-dipole attractions because carboxylic acid compounds are polar. And then because carboxylic acid has oxygen directly attached to a hydrogen, that means it can do some hydrogen bonding. Okay, and then with esters or halogenated hydrocarbons, so this would be your organic halides or alkyl halides, all means the same thing. Okay, so for these, the ester functional group is you have some sort of chain of carbon, okay, and then you have another chain of carbons. Okay, so for this, there we go. For this, it is going to have London forces, and it is going to be able to have some dipole-dipole attractions. However, because there's no hydrogen directly attached to one of these oxygens, there's not going to be any hydrogen bonding here. Okay? And that's going to be the same situation for the halogenated hydrocarbons. So for these, you're just going to have some sort of carbon chain and some halogen. So it could be something like fluorine. Okay, so again, everything has London forces. This is going to have dipole-dipole attractions. However, because there isn't a hydrogen directly attached to this fluorine, okay, you're not going to have those hydrogen bonding intermolecular forces present. So London forces, dipole-dipole. Okay, so essentially what we need to do is we just need to look at these and compare all of the intermolecular forces happening to help us order these from highest boiling point to lowest boiling point. So the substances that are going to have the highest boiling points are going to have the most intermolecular forces. So that's going to be these two here have all three. Okay. However, since they're tying, we need to figure out, okay, how are we going to figure out which one has more or has a higher boiling point? Okay. So if you're comparing two compounds, you can do it a couple of different ways. Okay. So one is if your compound is more polar, it'll have the higher boiling point because that will lead to stronger dipole-dipole attractions. Or you could also consider the larger the molecule, the higher the London forces, therefore the more intermolecular forces. Okay, so since carboxylic acid compounds tend to be more polar, so they have stronger dipole-dipole attractions compared to alcohols, and they're typically larger compounds just because they have the COOH compared to just the OH in alcohols. That's why the carboxylic acid is going to have the highest boiling point. So that's why I'm going to put it as number 1. Then alcohols are going to be the second highest. And at this point, now we just have to say, okay, this one over here has like the next most intermolecular forces. So I'm going to put that as 3. And then this aliphatic aliphatic compounds have the least amount of intermolecular forces. So they are going to have the lowest boiling points. All right. Example 2, we're doing the same thing. We got a list of compounds and we need to order them from highest boiling point to lowest boiling point. Okay, so now that we have some actual compounds, I do find it more helpful to just draw out the compounds to help compare. Okay, and actually, before we get to that, I'm just going to go back and I said out loud this point, I just didn't write it out. So if you have two or more compounds tying for the same amount of intermolecular forces, to decide, you can do it one of two ways there. You can either figure out which one's more polar or go towards the one or consider the one that has the higher mass as the one with more London forces. And because the London forces have a significant effect on boiling points, that is actually like the intermolecular force that usually decides which compound, if you have two compounds tying, will have the higher boiling point. Okay, so if you have two compounds or more tying for the same amount or the same types of intermolecular forces, the compound with the higher molecular mass will have the higher boiling point. So did I mention that polarity can play a part? Yes, however, London forces play a bigger part in determining boiling points compared to polarity. So that's why I'm writing out focus on the compound with the higher molecular mass having, or giving you the clue that it will have the higher boiling point. Okay. So let's draw out all these compounds. So C2H6, I'm just doing the line diagram. That's just this. Okay. So we have 2 carbons on either side, and then the implied hydrogens. Remember, each carbon has to have 4 bonds. So the implied hydrogens, there's 1, 2, 3 there, and 1, 2, 3 over there, for a total of 6. Okay. So this compound is going to be like that. This compound will look like this. This compound is going to be, there's 2 ways that you can draw it. You can either draw it like this, or since that's a little bit kind of tricky to see what's going on here, you could draw it, hang on, or, okay, that hydrogen right there, like that, okay. Or you could draw it like this. Okay, and I'm going to have to stick the last 2. So this one, I'm going to have to put it over here. And then this one over here, I'll put it right here. Okay, so based off of our previous notes here, we know that carboxylic acids, right, they're going to be the compounds that have the highest boiling points, then alcohols, then esters or halogenated hydrocarbons, and then aliphatic compounds are just carbon chains. Okay, so looking here, we have our carboxylic acid, so this is going to have the highest boiling point there. All right, so next in line is the alcohols. So this one's going to be having the second highest boiling point, and then in third place we've got esters or halogenated hydrocarbons. So keep in mind these are all tied for third place now. So now we need to go to this point where the higher the molecular mass, the higher the boiling point. So we need to figure out the molecular mass of each of these. So just as a reminder, these 2 drawings are referring to the same compound. They're just different styles of drawing the same compound. So the molecular mass for this compound is 60.06 grams per mole. Then over here, this is going to be 48.07 grams per mole. Then this is going to be 155.97 grams per mole. Okay, so looking at the molar masses, This compound has the highest molar mass out of the 3 that are tied, so I'm going to go 3, and then this one has the next highest molar mass, so 4, and then this one has the lightest molar mass, so then that's taken care of, and then our last substance is going to be ethane. Okay, so those are now all arranged according to boiling point from highest to lowest. All right, moving on to solubility. So water has 2 hydrogen bonds, and in order for a substance to have a high solubility in water, it should also be able to hydrogen bond. Now, some rules about solubility, which I've mentioned before, is like dissolves like. So in other words, polar dissolves polar. Nonpolar dissolves nonpolar. Okay? But within those rules, if you have a polar molecule that you're trying to dissolve in water, which can do hydrogen bonding, but the polar molecule that you're trying to dissolve in water can't do hydrogen bonding, that will decrease its solubility in water. Okay? So let's just write out the rule that I was talking about. General rule of solubility. Let's get rid of it. Like dissolves like. What does this mean? Polar substances dissolve other polar substances. Nonpolar dissolves nonpolar substances. Okay? But if you try to dissolve a nonpolar substance in a polar substance, it's not going to work out. Okay? Because that isn't like dissolving like. Alright, so polar molecules that don't have hydrogen bonding happening are only slightly soluble in water. Nonpolar molecules dissolve nonpolar solvents and are not soluble in water. Actually, I'm going to highlight this too. Okay, so some examples. Ethanol. It dissolves in water quite well because A, ethanol is polar, and B, it can do hydrogen bonding, so that's why it dissolves quite well in water, because water also is polar and also can do hydrogen bonding. Okay, wax, that can dissolve quite easily in gasoline because both substances are non-polar. However, wax and gasoline, they are not going to be able, or not going to be soluble in water because both wax and gasoline are non-polar. Water is polar. That will not mix together. Okay, because like I said, like dissolves like. Polar will only dissolve polar substances. Non-polar will only dissolve other non-polar substances. Okay, chloromethane, so CH3Cl, that is slightly soluble in water. The reason being is because, yeah, it's polar just like water. However, it can't do hydrogen bonding. That's why it's only slightly soluble in water. Okay, so we've got an example, and it wants us to put the names in the proper column. We can use some more than once. So we've got some names here: aromatics, alkenes, or alkanes, alkenes, alkynes, alcohol, which are large, small alcohols, carboxylic acids, large esters, small esters, and organic halides. Okay, so for the first one, we're kind of checking the solubility in water. Okay, so substances that are insoluble in water, okay, those are going to be your non-polar compounds. Okay, so non-polar is insoluble in water because water is polar. The compounds that are slightly soluble in water, those are going to be polar, but no hydrogen bonding. Okay, and then substances which are soluble in water, those are going to be your polar substances that have hydrogen bonding. Okay, so that's kind of what we're looking for each category here. Okay, so looking for nonpolar aromatics, that's definitely going to be nonpolar. So remember, aromatic compounds, those are compounds that have benzene in it, and benzene is nonpolar. Okay. Additionally, alkanes, alkenes, alkynes, those are just carbon chains that either have single bonds, double bonds, or triple bonds in them. Okay, those are all nonpolar. Okay, with large alcohols, okay, so a large alcohol, if I draw this out, is going to have like a really long tail on it. And remember that this tail is nonpolar. Okay, so with this, because it has a huge nonpolar section to it, I'm going to put it in insoluble in water. Okay. However, small alcohols, okay, because small alcohols will have a smaller kind of tail to them, so it's not as much of a nonpolar section to them, those are going to be way more soluble in water because they are more polar, okay, than large alcohols, and they can do hydrogen bonding. Okay. For carboxylic acids, those are going to be very soluble in water because they're polar and they can do hydrogen bonding. Okay. With large esters, so remember the functional group for esters is looking like this. Okay, so there's no hydrogen bonding. It could be polar, right? But because it's large, that means these chains are going to be quite long, and the carbon chains are going to be non-polar. So because there's large sections of these large esters that are going to have non-polar parts to them, quite large non-polar parts to them, that's why I'm going to put it in insoluble. Okay, with small esters, I'm going to put them in slightly soluble because, yeah, they're polar, and these chains here where you're going to have your non-polar sections, they aren't going to be as long, so they aren't going to hinder solubility as much. Okay, and then for organic halides there, for this, organic halides, they are going to be polar, but they can't do any hydrogen bonding, so we're going to put them here. All right. So with this next chart, we're going to be using the same list. However, it's going to be an opposite trend. The reason being is because we're checking the solubility in benzene. And since benzene is nonpolar, that's why the trend is going to be opposite, because our solvent is nonpolar now. In our first example, we had a polar solvent. Okay, so something that's insoluble in benzene, which is nonpolar, you are looking for something that's going to be polar and have hydrogen bonding. that will be very insoluble in benzene. Okay, slightly soluble in benzene will be a polar substance but no hydrogen bonding. And then soluble in benzene will be your nonpolar substances. Okay, so essentially this table is going to be like the flipped version of our initial table. Okay, so small alcohols and carboxylic acids, both of them are going to be polar, both are going to be able to do hydrogen bonding. Okay. With slightly soluble in benzene, those are going to be your small ester and your organic halides. Okay, and our nonpolar substances, those are our aromatics, alkanes, alkenes, alkynes, large alcohols, and large esters. Okay, moving on to extraction processes. Okay, so there's a couple of different ways that you can extract one compound from another compound. The first being solvent extraction. Okay, so solvent extraction, you're separating compounds based on their solubility in a certain substance. Okay, so if you have a mixture of a few different chemicals with different polarities, you can try to add a solvent that will allow one chemical in the mixture to dissolve in it, but not the other. Okay, with distillation, you're separating compounds based off of their boiling points. Okay, so you should know the general idea behind each of these here. So, for example, for distillation, let's say you take a solution of ethanol and water. Okay, so ethanol can dissolve in water, so that's why we have to use distillation in order to separate them, because ethanol is going to have a lower boiling point than water. Ethanol's boiling point is at 78 degrees, whereas water boils at 100 degrees. So if you take this distillation apparatus and heat up your solution to 78 degrees, essentially what will happen is your ethanol will boil off and then it'll go in here, which essentially what's happening here is you have cold water cooling it down so that your ethanol turns from a gas into a liquid, and then it just drips down into your collection round bottom flask. Okay, so ethanol will boil out first because it has a lower boiling point. Okay, so over here you'll have pure ethanol, whereas over here you'll have your ethanol / water mixture. Alright, now for fractional distillation, this is used when you're trying to separate different compounds out of crude oil. Okay, so when crude oil reaches the refinery, it's made up of many different molecules with different sizes. The different types of molecules need to be separated to form various petroleum products. So since larger compounds have higher boiling points than smaller ones, the molecules can be separated according to boiling point. So you do need to be aware of how a fractional distillation tower is going to work. So you need to know that this is going to separate compounds based off of their boiling points. Okay, so here we have our steam heat source. So the compounds that are going to boil off at the lower levels are going to be the compounds with the higher boiling points. Okay. So bigger compound or bigger molecule, higher boiling point. Okay, whereas as you go up through the fractional distillation tower, because we're getting farther and farther away from the heat source, the compounds that boil off here are going to be your smaller compounds with the lower boiling point because it's cooler up here. Okay, so over here it kind of talks about the fractional distillation process, just a little bit more detail. So crude oil enters the bottom of the tower and is heated to over 400 degrees. The long hydrocarbons such as waxes, asphalt, and lubricating oils do not boil at this temperature, and they stay to the bottom of the tower. Okay, so that you can see right down here. Okay. Smaller hydrocarbons, they're going to become gases and they will begin to slowly rise up the tower. The tower is going to be separated into stages with different temperatures, and when a hydrocarbon reaches a stage with the temperature of its boiling point, it's going to condense and then be removed. So that's how fractional distillation towers work. Okay, now after the crude oil is separated by the size, the fractions are further modified by processes called cracking and reforming. Okay, so what exactly is cracking? Cracking is just breaking carbon-carbon bonds by heating long chains of hydrocarbons under high pressure in the absence of air to form smaller hydrocarbons. Okay, so cracking, you could think of it as just breaking apart. Okay, there's various types of cracking. There's hydrocracking, catalytic cracking, steam cracking, etc. Okay, and they give some examples of steam cracking here. For this, don't worry about memorizing. The main idea is you need to know that cracking, what it does is you take long chains of hydrocarbons and break them apart into smaller chains. Okay, and you get a variety of different products from the cracking process. Okay, because not all the long chains of hydrocarbons are going to break in exactly the same spot. Okay, with reforming, that's a technique that uses heat, pressure, and catalyst to convert naturally occurring straight-chained hydrocarbons into a more useful form. So your products are going to include branched alkenes, cyclic alkanes, and aromatics. Okay, so this process, it usually involves the removal of hydrogen atoms. Okay, so essentially you're taking, in this example, we're just taking a chain and we're creating an aromatic ring here. Okay, so essentially what reforming is you're just taking a hydrocarbon and you're just making it into a more useful form, whether that's going from a straight chain into a ring or a straight chain into a branched alkane. Okay, this picture down below kind of tells you a little bit more about the process of what happens to fractional distillation products as they get further refined. Okay, so the main idea here is that you need to be able to relate properties of substances such as melting and boiling points, although we focused on boiling points, to the predicted intermolecular bonding in substances. So essentially, you're just going, the more intermolecular forces a substance has, the higher the boiling point or melting point it's going to have. Okay. Additionally, you should be able to compare both within a homologous series and among compounds with different functional groups, the boiling points and solubilities of examples of aliphatics, so carbon chains, aromatics, so things that have benzene in it, alcohols, and carboxylic acids.